Alright, good morning. Today we're going to be talking about section 5.4 entitled Parameters for Binomial Distributions. Let's start out the talk today. Let's say we suppose the probability of a boy in any birth is 0.7. Just suppose it. I'm going to let x, a random variable, equal the number of boys in 4 births. Alright? Successively applying our binomial probability formula, which on our calculator is the Binomial operator, we can find the probability of any number of boys in these 4 births. Well, any number of births from 0 to 4, of course. Alright, again, using this Binomial operator with n equal to 4, p equals to 0.7, and x ranging anything from 0 to 4, well, I can say the probability of 0 boys is going to be 0.0081. Again, we get there using our Binomial operator. Our Binomial operator for n equals 4. Probability of a boy in any one birth is 0.7. And for the 0 case, we plug in x equals 0. I can similarly grind this out for the probability of 1 boy. That's 0.0756. The probability of 2 boys is then 0.2646. Again, using the same Binomial operator and just changing the desired number of successes. And the probability of 3 boys is 0.4116. And of course, the probability of 4 boys would then be 0.2401. Alright, so we've exhausted all possibilities for our number of boys in 4 births, getting 5 different probabilities. I'm going to arrange these probabilities in a table fashion. And I can see, let me scroll down a little bit here. I can let x be my number of boys from 0 up to 4 and arrange my probabilities in table-like fashion. Give me a second to write these out again. 0.0081, 0.0756, 0.2646 for the 2 case, 0.4116 for the 3 case, so 4 there, and 0.2401 for the 4 case. Alright, as you may recall, this takes the shape of our first forays into Chapter 5. This is a probability distribution. Remember, a probability distribution distributes one unit of available probability amongst all possible values of a random variable. Now notice I left a little space here because I'm going to add in another word here. Not only is this a probability distribution, it is a binomial probability distribution because it's based on a binomial experiment. We've got a fixed number of trials, We've got 2 outcomes per trial. The probabilities are constant in each trial, and the probabilities are independent from trial to trial. All right, this is a binomial probability distribution, again, because it's based on outcomes of the binomial probability formula. Okay? Now, as we know from section 5.2, we can find means and standard deviations for probability distributions, but it's very tedious. I go back to yellow here. Recall. The mean of a probability distribution is summation x times p of x, and the standard deviation of a probability distribution is square root summation x squared times p of x minus the previously computed mean squared. And as we saw in section 5.2, working out these formulas here, these 2 formulas, can be a little bit cumbersome, depending on the situation. But I have good news. If you can justify a binomial experiment or a binomial probability distribution, these formulas are quite a bit easier. For a binomial probability distribution, mu, which heretofore has been figured out with summation x times p of x, is simply your number of trials times the probability of success in any one trial, little p. And sigma, your standard deviation for that probability distribution, is root npq. I think you'll agree with me, this formula is much simpler than this one, and this formula looks a lot simpler than this one. Alright, so for the above case, let's see, can I work this out? Kind of hard to get it all on one screen. For the above probability distribution, we see n was our number of births, n was 4, p, the probability of success in any one trial, was 0.7, and of course q is the probability of failure, and that's just the complement of p, 1 minus p, and that's 0.3. So if I try to work out the mean and the standard deviation for this probability distribution, if I use these formulas here, it's going to be very cumbersome. Right? If you can justify somehow you're using a binomial formula to grind these values out, we can use these 2 simplified formulas. Let's do it for this above probability distribution here. Well, mu is simply n times p. Well, n is 4 and p is 0.7. Really, that's all there is to it. And if I punch that out of my calculator, I get a 2.8. So the mean for the number of boys in 4 births, where the probability of boy is 0.7, that mean value is 2.8 boys. Similarly, the standard deviation for those number of boys in 4 births, it's root n times p times q. Now remember, little p is the probability of success in any one trial, and q is going to be the probability of failure in any one trial. Now if I punch this out of my calculator, I get 0.917. Let me check that. 4 square root 4 times 0.7 times 0.3. Yes, I do indeed get 0.917. So quite a bit easier than the old method. grinding things out, adding a third column, getting summation x squared times p of x, etc. a lot cleaner if you've got a binomial probability distribution. All right. Let me say, in warning, note that mu equals np and sigma equals root npq. These two formulas only work in a binomial probability distribution. The trouble is they're so much simpler, students try to use them often in non-binomial probability distributions. And of course, how do I spot a binomial probability distribution? Again, you've got to satisfy the four criteria. You've got a fixed number of trials, 2 outcomes per trial, probabilities are constant in each trial, and each trial is independent of any other trial. Let's look at example 1 on page 223. Let's see, can we read this here? Example 1 in page 223. Scroll down here, get the textbook here, you can probably see it on the screen here. The brand name of McDonald's has a 95% recognition rate based on data from Retail Marketing Group, etc. A special focus group consists of 12 randomly selected adults to be used for extensive market testing. For such random groups of 12, find the mean and standard deviation for the number of people who recognize the brand name of McDonald's. Alright. Go back to the screen here. Alright, so we're asking 12 people. Do you recognize the McDonald's brand name? The probability that any one person in this given information recognizes McDonald's is 0.95. Alright, they want the mean and the standard deviation. Well, simply, this mean is going to be n times p, which is going to be 12, times 0.95, which punches out to 11.4. The standard deviation for the number of people that recognize McDonald's is npq, root npq. So it's going to be the square root of n times p is 0.95 times q. Remember, q is the complement of p because there's only two possibilities for each trial, success or failure. And if I punch this out, I get a 0.75. Our book says 0.8. I'm going to call it a 0.75. Okay? Alright, I want to look back at the book here for a moment. I'm looking at example 2, unusual outcomes. Okay, they're still referring to example 1. It says for groups of 12, part A in example 2, for groups of 12 randomly selected people, use the range rule of thumb to find the minimum usual and maximum usual number of people who recognize the brand name of McDonald's. Alright, you recognize this jargon, hopefully, regarding usual and unusual outcomes. Let me scroll down a little bit here. Let me get a fresh screen here. This would be example 2A in section 5.4. Alright. Recall. Usual values in terms of mean and standard deviation are given these somewhat arbitrary appearing values, mu plus 2 sigma and mu minus 2 sigma. Well, we've already recorded mu as 11.4 in example 1 and sigma as 0.75 in example 1. So I claim values between these limits are going to be usual, and anything beyond high or low is going to be unusual. Okay? Alright, well, just ground out these limits according to the numbers I've been given. 11.4 minus 2 times 0.75 on the low end. And that punches out to, I'll call it a 9.9. And on the high end, mu plus 2 sigma, that's going to be 11.4 plus 2 times 0.75. And that turns out to be a 12.9. So anything within these boundaries for people who recognize McDonald's out of 12 is going to be considered usual, and anything beyond that will be, of course, be unusual. Alright, so these are the maximum and minimum, respectively, usual values for number of people in 12 that recognize the McDonald's brand name. Alright, part B then asks, in a group of 12, is it unusual to find 12 people who recognize the McDonald's names? Let me write that down. In a group of 12, is it unusual to find all 12 recognizing the McDonald's brand name? Well, again, 9.9 is our minimum value for usual values. 12.9 is our maximum value for usual values. And 12, who recognize McDonald's names, certainly does not put us in our unusual realm. All right, this falls in the usual realm of responses. All right, so I could surmise the conclusion like this. I'll say 9.9 is less than 12, which is indeed less than 12.9. So in that case, I'm within the boundaries of usual behavior, so I'll say it's not unusual to find 12 recognizing McDonald's. Okay? So pretty simple formulas, really, with some pretty powerful possibilities. And we'll look at example 3 in our textbook. Example 3 on page 224. Well, let's see. Example 3 refers to the chapter problem. Remember, each chapter starts out with a motivating example, a chapter type problem that we often refer to. And in this chapter problem, they talk about genetic type research. We've got 945 births. And in these 945 births, 879 of them are girls, and 66 of them are boys. All right, let's say we don't know this yet. Let's say we don't know the outcome yet, and I want to cite part A of example 3. Let me read example 3. Let's read it together. Right here in the bottom right. Part 3A I'm referring to, assuming that boys and girls are equally likely, use those simplified formulas to find the mean and standard deviation for the number of girls born of 945 babies. All right. Well, we've got a fixed number of trials, 545, right? I'm calling a girl a success, and I'm saying, well, what's the probability of girl here? Well, assuming boys and girls are equally likely, ignoring these experimental results for a moment, we're assuming boys and girls are equally likely, so the probability of one girl in any birth is 0.5. Alright, so I can find the mean and standard deviation quite easily because I've got a binomial experiment. Fixed number of trials, probability of success is constant in any trial, etc. So mu equals n times p, that's just 945 times 0.5, and that's going to be 472.5 girls. Alright, that's our theoretical mean for number of girls in 945 births based on this criteria. Sigma is root n times p times q. Now notice if p is 0.5, that means q is also 0.5. It's the complement of 0.5. And if I punch this out on my calculator, I get 15.4 girls. So there's my mean, and there's my standard deviation for the number of girls in these 945 births. Alright, let's go back to the book, read part B. Use the range rule of thumb to find the minimum usual number and the maximum usual number of girls born in 945 births, assuming that boys and girls are equally likely. Alright, so according to my schema, I can find a minimum and maximum value for usual number of girls in these 945 births. The lower bound for usual value is going to be mu minus 2 sigma. We're familiar with that, I hope. And that's going to be 472.5 minus 2 times 15.4 using the previously calculated values of mu and sigma. On the high end, I'll get mu plus 2 sigma. That's going to be 472.5 plus 2 times 15.4. And if I punch these out on my calculator, I get a lower bound for usualness of 441.7 girls and a maximum value of usualness of 503.3 girls. Okay, so this answers the question cited in part B. Let's look at part C now. Part C, the bottom of the screen, bottom right. The chapter problem described the XSort method of gender selection that resulted in 879 girls born in a group of 945 babies. Is 879 girls unusually high? Well, I think I see something happening here. If you've got 879 girls, that puts you way in the unusual range. And that would mean something is wrong with the assumption that the probability of boy or girl is the same. This tends to suggest that the treatment, the XSort treatment, is working. So not only is this unusual, I would call this highly unusual. Certainly much higher than any number of girls I would expect by chance. So this suggests the XSort method of determining gender of a child is working. Okay? Doesn't prove it, but certainly highly suggests it. Alright, this concludes section 5.4, parameters for binomial distribution, and that is all for today.